This is part 7 of the series Applications of Differentiation. In this section we're going to investigate a little bit more deeply increasing and decreasing functions. So if you look at this graph, if we move from left to right, you can see that this function is decreasing from this point to this point. The function is constant at this point, between these 2 points, and the function is increasing from this point on. Now this is easy for us to recognize by eye, but analytically a little bit more difficult, but not too much. If we take a look at the slope of the tangent line, that is f prime of x, you can see that the slope of the tangent line is going to be negative in this interval. So where the slope of the tangent line is negative, we can see that the function is decreasing. Where the slope of the tangent line is 0 or horizontal, we can see that the function is constant. And where the slope of the tangent line is positive, the function is increasing. So f prime of x is greater than 0. So stated more formally, a function f is increasing on an interval if for any two numbers x1 and x2 in the interval x1 is less than x2 implies f of x1 is less than f of x2. So increasing f of x1 is less than f of x2. So a value here is less than a value here. That implies that the function value at that x1 is going to be less than the function value at that x2. And likewise, a function f is decreasing on an interval if for any two numbers x1 and x2 in the interval x1 is less than x2 implies that x1 is greater than x2. So in other words, if we have an x here and an x here, so x1 here, x2 here, x1 is less than x2, the value of f at that x1 value is going to be greater than the value of the function at that x2 value. So the bottom line for this whole thing is we're looking at the slope of the tangent line. This is the formal definition of increasing and decreasing, but what it translates to is we're going to be dealing with the slope of the tangent line on a particular interval. If the slope is negative, it's decreasing. If the slope is positive, it's increasing. If the slope is 0, it is constant. So let's look at some applications of this. So in this example, we're going to find the open intervals on which the function x to the third minus 3/2 x squared is increasing or decreasing. Now the way we're going to do this is we're going to employ a neat little process called the first derivative test. And so obviously with the first derivative test, we're going to need the first derivative of the function. So let's go ahead and do that. And we can say f prime of x equals 3x squared minus 3/2, we're going to use the constant rule, times 2x. Well, this 2 cancels that 2, so we have 3x squared minus 3x. There's our first derivative. Now what we're going to do is we want to determine where the function is increasing and decreasing. And we saw that the function is decreasing where the slope of the tangent line is negative, and the function is increasing where the slope of the tangent line is positive. But the places where that changes is a real issue for us. So what we're really looking at is if we want to determine where a function is increasing and decreasing, we know that at the extreme values, the slope of the tangent line is 0. So it makes sense then that we're going to be looking for our critical numbers, because to the left of this critical number, the slope of the tangent line is positive, therefore the function is increasing. To the right, it's negative, therefore the function is decreasing. Likewise, to the left of this point, the function is decreasing, and to the right, the function is increasing. So what we really want to find is our critical numbers. So let's set this equal to 0 and see where that exists. So 0 equals 3x. We're factoring out of 3x. We have x minus 1. So our critical numbers are 0 and 1. So we know that we're going to have some change in increasing or decreasing at those values. So those are going to be our anchor values. So we'll put 0 here and 1 here. And now we're going to employ a theorem from the past, the intermediate value theorem, that tells us that the function, if the function is continuous, it has to take on all values in between these values. So we can look at any point in here, and all the points in this interval are going to have the same characteristic. So let's pick -1 as our test value here. And likewise, in between 0 and 1, let's pick 0.5. And between 1 and infinity, let's pick 2. You want to pick your test values at easy values to evaluate. You don't want to pick crazy numbers because that just makes your life more difficult. So now what we're going to do is we're going to evaluate the first derivative. This first derivative function, we can use this one here to evaluate these test values. That's why it's called the first derivative test. So we're going to evaluate the first derivative at our test values. We're not going to evaluate it here because we know the first derivative is 0 at 0 and 1. So at -1, this function has a value of 6. 6 is positive, so what I'm going to do is I'm going to make a positive sloped line segment there to indicate that the function is increasing on that interval. Then I'm going to go to 0.5 and evaluate this function at 0.5, and it's negative. So I'm going to make a negative slope segment indicating the function is decreasing, and then I'm going to evaluate at 2, and that's positive. So we know our function is increasing on this interval and decreasing on this. So we're increasing on the interval -infinity to 0, non-inclusive, because at 0 it's constant, and on the interval 1, non-inclusive, to infinity. And the function is decreasing on the interval 0 to 1. Simple test there. Now let's look at another example. Now in this example, we're going a little beyond just finding the intervals of increasing and decreasing. We're going to find the relative extrema of the function. So let's go ahead and take our derivative. F prime of x is 1/2. That's the derivative of the first term. The derivative of sine is cosine. And we've got to find our critical numbers now. So we set this equal to 0. Cos x equals 1/2. So to determine the value of cosine at 1/2, we need to know our unit circle values. So let's just write it up here. Cosine is positive here and down here. Cosine is the x. So first and fourth quadrants. And it just so happens that cos is 1/2 at pi over 3 and 5 pi over 3. So our x value is going to be pi over 3 and 5 pi over 3. Bad 3. All right, now we go ahead and write. Those are our anchor values. And we write pi over 3 and 5 pi pi over 3. So now we need test values. Pi over 3 is up here, so something below that would be pi over 4. So we'll write it pi over 4. Now I like to write my test values lower than my anchor values simply because sometimes it's easy to get confused with which value you're evaluating the function at. So pi over 4 greater than pi over 4, we can say pi over 2, we can say pi, we can say anything we want. So let's just pick pi. Pi will be good. And then 5 pi over 3 is over here. So we need a number to the outside of 5 pi over 3. And 5 pi over 3 is equivalent to 10 pi over 6. So let's just pick 11 pi over 6 because pi over 6 is an easy one to evaluate. So let's evaluate the first derivative at these values. So 1/2 minus cosine of pi over 2, or pi over 4, is the square root of 2 over 2, which is negative. So we have a negative segment here. Evaluate this function at pi, and it comes out to positive. So this is positive, and 11 pi over 6 is going to be negative again. And so now what we can see is a different artifact from this first derivative test. If you look at this, this kind of sort of looks like a function doing this. And so we can infer that this point is a minimum and this point is a maximum. It makes it nice and clean for us. So in fact, this is a minimum and this is a max. And so our minimum value is going to be at pi over 3. Putting pi over 3 into this function gives us pi over 6 minus square root of 3 over 2. This is approximately negative 0.342. This is the exact value. That's our minimum. And our maximum is going to be 5 pi over 3. And we're going to be at 5 pi over 6 plus square root of 3 over 2. This value is 3.484. And so that's our max. And that's a simple way to use the first derivative test. Let's look at another example.